Welcome back to our NestJS series. Today, we are evolving our application from a basic prototype into a data-driven system integrated with a production database. To follow along with this implementation, you will need two tools ready: a running Postgres database instance and an API testing client like Postman or Insomnia. This diagram maps a request's journey through NestJS. Data moves from the client through the validation pipe, controller, service, repository, and into the Postgres database. The validation pipe blocks malformed data at the entry point, ensuring incorrect data never reaches our core logic. Establishing clear boundaries between layers allows multiple teams to work on the same codebase, while keeping the application maintainable and testable as the system grows. We begin by installing our infrastructure dependencies. You will need the type-orm package, which provides our database abstraction layer, and the Postgres driver to enable communication between the two systems. Once the packages are installed, we configure the type-orm module in the root of the application. This setup includes your database host, port, and credentials required to open a stable connection. There is a critical setting here called synchronize. While it is useful during development to automatically update your tables, you should never enable this in production, or you risk an accidental schema reset that could cause you to lose production data. To structure our data, we use an entity. In NestJS, an entity is a TypeScript class that defines the specific shape of a database table. We use decorators to define the mapping. The primary generated column decorator creates our unique ID, while the column decorator maps our class properties directly to the columns in our Postgres table. Defining the schema in TypeScript ensures that our application code and our database structure stay perfectly synchronized, without the need for manual SQL scripts. Before the data reaches the database, we need to enforce a contract for incoming requests. We do this using a data transfer object, or DTO. By adding validation decorators to the DTO properties, we can enforce strict rules, such as ensuring a field is a string or blocking requests that submit empty values. For these rules to take effect, you must find the global validation pipe in your main entry file. Without this step, your DTOs will not intercept or filter any incoming data. This illustrates the difference. On the left, an unvalidated request flows through the system and causes a database error. On the right, the DTO identifies the bad data and immediately returns a 400 error to the client, keeping the system stable. Validating data at the system boundary prevents unpredictable state errors and ensures your application only processes information that meets your requirements. To make our entity usable, we must register it within its feature module. This registration allows the NestJS dependency injection system to provide a repository instance where it is needed. We use the repository pattern to interact with data. The service layer coordinates logic and delegates specific operations to the repository. You establish this connection by injecting the repository into the service constructor, giving it full access to type-orm's database methods. The controller then accesses the router. It maps incoming HTTP requests, like POST or GET, to the corresponding logic in our service. We can also add error handling here. If a request targets a record ID that does not exist in the database, our service will throw a not found exception, which NestJS automatically converts into a proper 404 response. This pattern keeps the controller focused strictly on HTTP traffic, while the service handles the core business logic and data persistence. Now we can verify the entire flow. We have our API client on the left and our live Postgres table on the right. When we execute a valid POST request, the server processes the data and returns a 201 created status, including the new ID generated by the database. Looking at our database viewer, we can see that the data has been successfully written into the correct columns in our Postgres table. Finally, if we attempt to get a record with an invalid ID, we receive a clean 404 error, confirming our exception handling is functioning as expected. The application now has a validated data flow and a permanent persistence layer. Currently, these endpoints are open to anyone, so in the next phase, we will implement JWT authentication to secure the API.
Enhance your coding skills with us. Don't forget to subscribe to Code 5 Food for the latest updates and tutorials.